Hello and welcome back after the short break. We only have final two talks of the day today. The next talk will be presented by Stefan and Javier. Stefan's a long-term employee from Intel. He has been a big contributor to Blender for a while, and and so has Avia, and they will be presenting their a talk on the new SYCL cross vendor backend for the Blender cycles. Back to you. Thank you.
Thank you. So here is the agenda. Stefan will cover the first part, introducing you about Blender and cycles with some code overview, and we'll cover how we are using experimental but still critical extensions in Blender that do provide really key features for use case. And I'll cover the end, talking about how we maintain and ship Blender with SYCL support, and how you can also get a multi-vendor build using SYCL. And we'll also cover a few performance results that we measured on our machines.
So just as a quick introduction about Blender and cycles, so Blender itself is a 3D content creation application. It's been used mostly for media and entertainment, and it comes with, it's been really popular. It's open source and sort of just slowly evolving to becoming a standard application in that area. It ships with two render engines. One is called Eevee. It's built modeled more after game engines, and it's running on rasterization hardware. Currently mostly using OpenCL. There are Vulkan and Metal backends in the works. And the other render engine that they have is a final frame render called Cycles that is using path tracing for photorealistic rendering, which means it's not real time. It can take up to hours per frame. And that is written for both CPU and GPU using just C++ and not relying on any rasterization hardware. It's also been popular as a benchmark. And on opendata.blender.org, you can see a lot of results that users submitted for various hardware that they have. And it's also, the tech press is also using it a lot lately for just testing new hardware. One thing they do is they support multiple versions in parallel. There's always a sort of latest shipping release, and they have long-term support versions that Blender started shipping and supporting for studios that have a production that is running, and they need bug fixes but don't want to have anything change in what they're working on. You cannot just, in the middle of production, change how things work. And they're targeting a wide variety of hardware. So from the hobbyist who is at home with his budget machine to workstations for visual artists and even data center. So it's a big stretch that they're trying to cover. So Cycles, as I said earlier, is a path tracing, physically based render engine, which became in the last 10 years sort of the standard for visual production. It was introduced in 2011, and back then it was written as CPU code and what CUDA supported at the time. And the initial implementation was just one large kernel, so it was just one giant thing that did the entire rendering front to back. In 2021, it was refactored to become it's usually called a wavefront or microkernel approach, which splits the rendering into several steps. So you can split out the intersection into one kernel, which is finding what geometry is visible. Then you have the shading and lighting in a different one, some sorting in between. And that helps you get higher occupancy because your rays may not always, or your paths may not always have the same length that you trace through a scene. They can hit different objects, which give you, again, code divergence in terms of the execution of the shaders, and also really random memory access is also not beneficial. Reducing the kernels also gives you faster compile times. It could be really long in the beginning, and also it lowers the register pressure. Even though, as we'll see, there's still some pretty large kernels left, even though it's been split up into smaller chunks now. Now, the cross-platform hardware support, GPU support, started in around 2015 with OpenCL support. And that already had to split, not necessarily for the performance reasons, but simply because the OpenCL compilers that were shipping at the time were actually not able to handle that full kernel and crash when compiling or produce non-working code. So it already had to be split up back then, and it was still unstable, always required some work. Like you had it working on one platform, it would not work on the other. New features got introduced, and then the OpenCL backend wouldn't work anymore. They had to be turned off. And it became too separate from the CUDA code. It was getting harder and harder to maintain. So in a refactor in 21, they actually removed support for OpenCL and Blender. We'll hear why they didn't like it. And so the 3.0 release was with CUDA, CPU and HIP support. And for Intel GPUs, then was working Nikita here and Xavier mostly, that they added a SYCL backend in 2022 for the Intel Arc GPUs. Now the code, despite targeting all these different platforms, actually very legible and not too complicated for what makes the cross-platform part. It's pretty much just straight C++ in headers that then are included into a CPU file or in a CUDA file or in a SYCL C++ file. And it comprises now 36 different kernels, some really small, just little sort, some really big. And the state in between that is being stored between those kernels is sorted periodically and compacted so that when a lane runs empty, these empty jobs are being removed, so you don't have idling cores, and also the sorting helps with the coherence. So there's very little difference between those targets. The most backend specific code is the boilerplate code around it, managing buffers, managing memory, and queuing kernels. This is actually a simplified kernel graph. It's actually more complicated than that. The important one is here that it's basically going in this loop where you trace rays, sort them, or you trace rays, get the intersections, sort them, and then either shape surfaces, then go back to the next intersection, and so on and so on until your ray terminates, and then you can write to when you write out to the buffer. As a little impression of how we're doing. This is these are just some of the defines that are used to create the cross-platform abstraction. So there's basically just a define for a ballot, and that then goes to a different backend implementation. This is the SYCL version of a ballot. CUDA has a different one. CPU doesn't need one running single-threaded. Likewise, these thread IDs map to the corresponding CUDA calls. In this case, it's SYCL call. Also on the CPU, these just return one or are not even in use. And for launching kernels, we had to actually do something backwards a bit. Since the way that kernels are launched in the CUDA backend is just more like OpenCL, where you pass in void pointers and just very simple non-type safe arguments to the kernel. And SYCL doesn't really do that, so we had to create a little bit of kernel macro template magic to actually get from what is just an array of void pointers back to typed kernel arguments. And the largest kernel that we have is around 180,000 instructions. Are these the final compiled instructions, or?
Yep.
Okay. Not C++ code.
No.
Okay. But this is sort of the big heavy work that's the bottleneck for all the backends. It has to execute these user-generated shader graphs, and it's executing them in a stack-based virtual machine. That is a float 255 size stack, so it doesn't fit in the registers. It already has to spill somewhere, and it has a switch statement for 98 different node types. These are the sort of instructions that the virtual machine knows. Pre-sorting it by shader ID can reduce the divergence, but it's still a pretty heavy task and doesn't really work as well on GPUs as you would wish it to be. There's lots of cache misses and divergence still. It also creates a high register pressure, and even though we do sort, there's still, due to the nature of the Monte Carlo algorithm, there's intentional randomness introduced, which always causes divergence again. It's because it has long compile times, produces large binaries. It's not a fun kernel to work with. We did use the help of a few extensions here to get the, especially when we started out with the Intel backend that we had, we wanted to also see like, how does this actually work with NVIDIA and AMD hardware, even though they have separate backends already written in CUDA and HIP. We were curious to see what does SYCL do on these platforms. And there's a few extensions that we could use that help us there. Bindless textures were good because they actually give us access to the texture sampling hardware, which is there on the CPU on GPUs, but there's no direct SYCL support other than that extension, and it's complex to re-implement that. Otherwise, you could implement texture sampling by yourself, but leveraging hardware is better for performance and code size and whatnot. And device globals, I'll talk about those a bit. Free memory is also interesting to query because we're working sometimes with large data sets, and then it's important to determine as the application what goes on to device memory, what stays in host memory, as opposed to leaving it to the driver. And then there's a few smaller, still useful extensions that we used. Vulkan Inrob is for display. So bindless textures were necessary because the number of textures otherwise would need to be known at compile time if you use these SYCL images, which we don't. This is user-authored content. And we don't get the texture cache sometimes. We don't get fixed function hardware. So this helps us reduce the lines of code dramatically and increase performance. And there's going to be a talk on Friday about giving you more details about bindless textures in SYCL. Device globals were important for the CUDA backend, especially because NVIDIA hardware has separate constant cache that in cycles is being used for passing in arguments and certain important pointers. And our SYCL implementation didn't do this in the beginning because this weren't really these global variables in SYCL. So we had to put them into a wrapper class, but that generated extra indirect lookups, and it ended up in global memory, not in that constant memory. And with device globals, that could be changed, and it simplified the code, made it a bit more CUDA-like, and also gave some performance improvements. And by being more explicit about what this is intended to be, that it's constant memory and global, we're also giving compilers more room to optimize.
Thanks, Stefan. So now that we've discussed a little bit of the actual code implementation, the kernel side, I'd like to step back a little bit and discuss about how we maintain and ship Blender with SYCL, how all the pieces come together. I mean, Blender is an open source application which is targeting mainly client devices, so workstations, laptops. So I've only been working with client platforms, but my point of view is that's a bit more complicated than to support one specific machine or data center. And you can't really let anybody play with environment variables, install dependencies and whatever. I mean, at this stage, people already have removed the application because it doesn't work for them. Or even reinstalling the driver, changing driver, disabling a device. All this is really out of picture. The actual execution environment is just uncontrollable. So we have to deal with that. And it's not something that I've seen people implementing SYCL, providing compilers actually put enough thoughts in. So it's often that I have to end up opening pull request fixes myself and try to improve the situation there. So anyway, we have on Blender side, we have a developer build environment. That's almost easy. We have a source code targeting SYCL for Intel GPUs initially. We have libraries being integrated, and some of them are also using SYCL. So the biggest, most important one here is Embry, done by Intel, and that's the one we need to be able to use the hardware ray tracing on Intel GPUs. And for hardware ray tracing, one important thing to note is that we definitely need to be able to call really the API from inline from Blender's own kernels. So we can't really go through host or change runtimes or have synchronization or anything that would, even code stack would ruin performance here. So we need inline calls to hardware instructions in final assembly. And we do so by linking with Embry. We also have OpenImage denoise, which is using SYCL for Intel GPUs. It's a library that provides the denoising pass after rendering. It's quite separate and self-contained. Still, when using SYCL and you enumerate something like kernel bundle, you can see the OpenImage denoise kernels. So you need to pay attention to that if you're playing with kernel bundles from the device code. From developer environment, we're using the OneAPI DPC process compiler, the open source version. I'll say more why this choice in a coming slide. Note that this compiler, we're using it only for the kernel, the part of the code that provides the kernel and launches the kernel, which means for the rest of Blender, which is huge and is not made only to run cycles on Intel GPUs, it stays compiled with the host compiler. On Windows, it's Visual Studio, and on Linux, it's GCC. On Mac, it's Clang. The point is, a lot of the SYCL device code, it's actually compiled with Visual Studio. It's not compiled with OneAPI DPC process compiler. Still needs to work. I mean, all the part that does memory transfer and so on, it's then not compiled by the DPC process compiler itself. And that's not a scenario that's often well covered, but still. It's important here in this case because Blender will not switch the whole compiler for all the libraries, for everything, just for one GPU backend, while Blender needs to target all kinds of vendors. At build time, we're also using the Intel GPU's compiler to produce binaries because, as Stefan said many times, kernels are big. So if you need a few minutes of compile time, more than 10 gigabytes of memory, and even on a beefy desktop to generate kernels, that's not something you want to actually get tried on a thin laptop that somebody just bought. But that's using a GPU compiler also helps us controlling a little bit what the GPU compiler does. Well, we can control the version because once it's on in an uncontrolled environment, like some random user's laptop, then you can run into issues with various driver versions. It's good that we're able to fix that. So it's one less moving parts. There are enough moving parts. Now it comes to the application package once it's built. That's what will get shipped as a big package on the website. So it contains the application binaries, of course, and also all the dependencies. And when I say all the dependencies, that's just everything that's not part of the OS or drivers needs to ship with Blender. You can't tell people to download the third-party package or whatever. You can't tell that. You can't ask and you can't expect. So it contains also the SYCL runtime and a few layers underneath. So the actual API layer between the application package and the OS and drivers is the level 0 API. There are many reasons for that. But level 0 API provides rather stable C ABI that does provide compatibilities across driver versions, newer, older, future, much more than different versions of the SYCL runtime with a C++ API, that with incompatibilities across compilers, with various different versions, with open source versus proprietary versions, and I can go on and on. And but we need to distribute it as part of Blender. One exception to that is the case of Linux distributions, because Blender is open source. People can also build and distribute Blender on their own. And Linux distributions can sometimes do that, providing their own Blender package on their repositories. And in that case, it's very often that they will choose themselves to split it and distribute as separate shared libraries. So to have just one SYCL runtime in the repository that Blender will use and so on. That's great, it works. Just know that if you encounter bugs on such packages, it's best to first report the bugs to distribution maintainers. we help keeping it running, but yeah, you can also run into new kind of issues. So it's best if you first have a look at does it even reproduce with regular Blender packages? Sometimes it doesn't. Yeah, and on the driver packages, I've included level 0 loader, which is very supposedly only one in the system, and then various level 0 runtimes. Well, usually one for just one GPU. You can still have GPU compiler being triggered if you have incompatible binaries. For example, when using a version of Blender that predates the introduction of a new GPU. So then the binaries may get recompiled from the this purview that's inside Blender binaries. Because now there are no new releases of old Blender versions for each new GPU that gets released. So it's okay. I know it's a huge list of requirements. No need to go through them all, but I wanted to write them somewhere. And points 1 to 3 are really the biggest explanation. The explanation why we're using the open source version of the One API DPC++ compiler. I mean, Blender is open source, GPLB free. It needs to ship things that are open source, and we ship the SYCL runtime. So that means we need an open source SYCL runtime. That's as simple as it is. So it is rebuilt on Blender sites on Blender infrastructure. It provides other good things that are not part of the Intel One API distribution, like compatibility with older glibc version. Even in the first version, actually, we had to support the old C++ ABI in 2022. It was a lot of fun. So to go to this extent. Nowadays, it's better. We don't different C++ ABI, but still old glibc support requires that we build on old enough target. So yeah, for Blender, as it's targeting client applications, it's critical that we can really have good support with old drivers, new drivers, and really needs to be guaranteed. Other important features that we're using, so we need to build multiple IoT GPU binaries per target because we want to support more than just one GPU. There is only one build of Blender that gets distributed on the website for 64-bit Windows and one for 64-bit Linux. Right now, it's actually missing for AMD and NVIDIA platforms, so that would be quite a blocker. We have the device binaries compression because, well, we have multiple IoT binaries, then it grows. I think we can count uncompressed like 30 megs per set of kernel, which while the overall Blender package is maybe 300 megs right now. Yeah, so compression needs to be there. It has been enabled recently. And for best performance, we need hardware ray tracing. So right now, it's only available on Intel GPUs for Embry when you're using SYCL. If you want to use it for other hardware vendors, then nothing is really compatible with SYCL at the moment. Talking about how we integrate, so as said, we have the host compiler compiling Blender, DPC++ compiling just a library providing the kernels. So we do call Clang ++ fsql separately through CMake custom comment. We have CMake variables to control which SYCL targets you want and the options for each SYCL target you want. So by default, we compile only for Intel GPUs, but actually with everything that's out of the box, you can already compile for AMD and NVIDIA. It's been the case since 2022, actually, with the first release, but yeah, not many people actually used it. We used it from time to time. Sometimes we broke it. I had to fix a few things here and there, but nothing big. It's been rather stable support. So if you have, you can get your DPC+ compiler from Intel with the CodePlay plugins, or recompile it yourself from GitHub to have CUDA and HIP support. Then you set the appropriate Blender options. And at runtimes, you add one environment variable to other using devices that aren't officially supported by Blender. We use this variable for all kinds of reasons, mainly to prevent from running on very old Intel GPUs that are not supported. Good thing when running on NVIDIA, not highlighted enough, I guess, is that actually all the tools work well. We can have source code mapping to SAS through, even if we are using SYCL and not directly CUDA, which is nice. To give a few data points on the performance we're reaching at the moment on my machine with the RTX 3080, recent Blender source code, just one trick to add to limit the number of registers used by PTX to just 128. We get more than 95% of the native speed that we get with CUDA. If we look at the execution per kernel, like with almost 20 kernels, okay, maybe it's well, just give you a picture of many kernels, but we can simplify it between what does intersection, what does not do intersection. When everything is in software, it's roughly half and half. And yeah, we can see it's more or less competitive. Yeah. So hardware retracing is still an important topic. That's the part that will accelerate intersection kernels greatly. And that's not available for SYCL for other platforms than Intel at the moment. But so you understand what we're talking about in terms of practical implication, you can look at the numbers here. So it's execution time in seconds. We've been able to also try on HIP on AMD platforms. Here it's a little bit slower than what we currently get with CUDA, but honestly, we have done zero tuning, zero optimization. We just tried how it was out of the box. So I would say it's not too bad as a start. So yeah, to conclude, we have SYCL shipping production on an application that actually runs on many types of devices. We haven't introduced that many bugs. People haven't complained that much, so I guess it's a success. Performance is also good. Yeah, we had a few fun bugs because you need to know that Blender can be used, can use a lot of plugins, but Blender itself can be also used as plugin, and sometimes even using fastmath in the kernel library would lead to the FPU state of a process to be switched, which would kill Mesa rendering on Linux. So we had some kind of fun bugs, but everything got solved in the end. Your implementation is open source. You can just check it up. You can try running it on your machine if you have AMD, NVIDIA, or Intel GPU that is recent. Something to note for implementers or users, don't overlook the extensions to SYCL. Some of them are just critical in Blender's case. And that's it. We can go to question sides. Yeah. While we wait for questions, there are a few tips and tricks we had no idea what to put in the presentation, so we got this in the end.
Thank you for the talk. And I don't envy your job. This maintenance seems to be nightmarish, so so a little compassion for you.
Thanks.
I have a question. When you saw all this if def and everything, like to support HIP, AMD, more at the runtime level, did you ever thought about, because every time when I see this slide, it looks like you are yourself, mostly the parallel for to submit, you are yourself maintaining kind of a fork of SYCL, right? It looks like you are using your own abstraction layer to be able to submit stuff and everything. And what is your stance on maybe using the SYCL API and re-implementing everything, your own kind of backend for AMD, like a minimal SYCL implementation for your use case for AMD, HIP, and everything, so at least you use SYCL like as a stable internal API, something like that.
So your question is about replacing the native backends with SYCL, or
maybe just for you is like, okay, if I am a system where I have SYCL, I can use SYCL, but if SYCL is not installed, I will just kind of fall back to my own implementation where I use CUDA memcopy and all of these kind of things. It's like, because you have already your own portable layers. This is just what I want to say, because you need to submit kernel, you need to do memcopy, you need to do all these kind of things. So you are your own function who do.
I mean, maybe why not using level 0 or something lower level even, or?
Yeah, but yeah, I guess because you have C++ or I don't know. Yeah. Yeah, we can. Sorry, I'm not clear, but we can discuss later.
Yeah, it's not. I mean, this part, like memory transfers, enqueuing kernels, it's not the complicated part, and that's not what we would be interested. I mean, if we were to do the lower implementation for this part, we would be missing the huge part, which is actually be running the C++ kernel codes with bindless textures. Where there is a lot of things that we are relying on within the kernels. Then that's provided by higher level framework like SYCL. And so I don't see how we would be able to re-implement all of it.
Yeah. So you are far more interested in not really in the runtime, but more in the kernel language.
Yeah. And the kernel is a complex part. I mean, 180K instructions for the biggest ones. It's
yeah.
I remember working on Blender a long time back, and the kernel size was a big problem. And it was interesting seeing even it reflected in the packaging, some of the packaging decisions. Has the Blender team considered, like, is it even possible to simplify the kernel, which would simplify your packaging and might make it portable to more devices also?
This is the simplified kernel, to be honest. The original kernel was bigger. The mega kernel was really big, and now it's been split out a bit more. There's separate shading kernels depending on what features being used. So if you use manifold next event estimation, you get this shading kernel. If you don't use, you get a smaller kernel. So these things are already there. It's in everyone's interest to split these down as small as they can. Like every compiler is struggling with it. It's not just that SYCL compilers would be at the limit of it. I've been working on the cycles since its inception almost. And in the beginning, it was really like you add a feature and suddenly CUDA couldn't compile it anymore. You had to play with inlining until it would actually compile again. Then you had the same thing again with OpenCL. When OpenCL came in, you had to play a lot with what you inline, what you not inline, which feature can you use, unrolling, everything would just be right at the breakup of the kernels. And then again, it came again with Metal and with SYCL. So, and this is about as small as it gets for now, because it really has to be very, very featureful and cover a wide variety of use cases.
One way to get it smaller is to get more into adaptive compilation, deactivate things that you know about. I'm not going to use when rendering a scene, but in the end, you can always find somebody who will just use everything.
Mm-hmm.
So
yeah, I mean, we did we have experiments with specialization constants that would then shut off parts of the code at runtime. These are still not in because the JIT time, because then you would actually JIT compile the whole thing again. And those times are still prohibitively long to be like a user would just check one box and would have to wait minutes until the JIT compile would be through to get this new kernel with the features that are needed.
We have only time for one last question.
Yeah, you mentioned the hardware feature. So you need an extension to for that hardware feature, right? That's called
hardware retracing. Yes. The intersections in hardware, we do need some kind of hardware implementation.
Yeah. Do you have like a performance before and after with that hardware?
So we have it as an example with on NVIDIA. Yeah, right here. So you see all the kernels doing intersections in orange.
So again, is the
you see the speed up that they get by going to optics, which is NVIDIA's framework to do.
Is it Intel specific? I mean, the hardware? No.
Now here it's without SYCL. Here it's comparing CUDA and optics. So native CUDA and native optics.
Who is that hardware feature? Is you mentioned it is Erin or something. There's a feature.
IRA?
Yeah.
IRA is a higher level framework, but it's optics here that does provide the feature.
Oh, okay. Gotcha. Thank you.